Uh, I am going to talk about the gravitational wave sources. I am Rajesh Nayak from ISAR Calcutta and part of Indigo consortium. So, overall plan of the talk is I am going to start with the quadrupole formula. That is our starting point. You must have already introduced to the linearized field and quadrupole formula. So, I am going to start from that point and go on with the how our 2-point particle emit gravitational waves. So, in this gives a broad overview of type of sources in the gravitational waves, then go on to specific cases in little more details. This includes compact binaries such as binary black hole or neutron stars, which are most popular sources, then rotating neutron stars and gravitational radiation from supernova and from the entire universe itself. Let us start with the quadrupole formula, which is basically summarized here, which gives the amplitude of gravitational wave radiation emitted in the TT gauge. The TT stand for the transverse traceless gauge. The important point to observe here is the coupling coefficient, which is two fundamental constants come here is G and C, the Newton's gravitational constant and the velocity of light, and the factor which turns out to be 10 to the power minus 45 MKS units, and that is very small. So, this is one of the main problem related to this field. That means the gravitational waves cannot be generated in the lab or day to day life, because even if you generate a quadrupole acceleration, which is a third term there, even if it is of the order of thousands, even then you would generate a amplitude of only 10 to the power 40 or 35 of that order. So, you need astrophysical sources of gravitational waves. That is the first point to be seen. The second one is a distance from the source. It is usual that amplitude falls off as 1 by r. The last term which you see is what we call the quadrupole momentum tensor, which is a trace free part TT gauge, which is given in. So, it is essentially the quadrupole tensor, which is defined through the moment of inertia whose trace is removed, and it is corresponds to Newtonian quadrupole tensor related to density through the equation given below. So, essentially you can, for a given density distribution, you can calculate the quadrupole momentum and take the second derivative of that. That in turns will tell you the how much gravitational wave amplitude is emitted. So, this is essentially is a exercise which we are going through while calculating the gravitational wave radiation. In addition, you also have this last term, which is T minus R C, which we call the retarded time. It is not only a time at which radiation is emitted important, it is also the spatial location, which we also call the phase in a way, which is important. So, this essentially determine the gravitational wave emitted from a quadrupole moment mass distribution, and it is directly related to double derivative of the quadrupole momentum tensor. Another important quantity in this case is the energy emitted in gravitational waves, or the luminosity of gravitational wave source, which is again related to third derivative of the quadrupole momentum tensor, and one can calculate average it over a given orbit or given time and see how much radiation is emitted. The energy is continuously radiated in terms of gravitational waves, and that is what we observe from far off source. So, this being a formula, let us try a small toy problem in which we apply this quadrupole formula to a 2-point masses. We idealize this as a 2-point masses. This could be a 2 stars or 1 star, 1 black hole, or any combination of them, which are separated by a distance r, and they go around with each other or they are rotated at the angular frequency some omega, and we calculate or estimate how much radiation is emitted with this system. So, radiation from 2-point masses, the first we have to write down the quadrupole momentum. For that we need to know the energy momentum tensor or moment of inertia tensor. So, for that we need to know the location. You can for an orbiting particle separated by a distance of r, you can write them as follows: cos theta and sin theta, which basically tells where they are in the orbit, and then you can compute the this thing. The theta is basically omega t. Omega is the angular velocity with which the system is rotating. You can usually write this in terms of a moment of inertia frame or a center of mass frame. That is why the notion of mu and reduced mass and m1 coming. So, that we will come back to that later. Currently, we simply take them as a 2 mass separated by a distance and rotated at some angular momentum, angular frequency omega. So, their density for this is essentially a delta function at the where the point masses are there and the 0 elsewhere. This we need to plug it into the radiation of point masses, and we can calculate the moment of inertia tensor, which is essentially given by these 3 equation, 3 non-vanishing component of Ixx, Iyy and Ixy, and you always see they are written as a cos 2 omega t is coming. This is because of the quadrupole nature of that. And once you have the moment of inertia, you can also calculate the quadrupole momentum of these 2-point masses, which is also given by this equation. Should see that it is essentially reduced from the moment of inertia tensor, and you can find the second derivative of this, which need to be directly plugged into the radiation formula or quadrupole formula. And important point to see is that the amplitude of the gravitational radiation is emitted is depends on the omega square r square, and one can approximately say that the velocity of the system is omega times r in a rotating frame. This gives us that the amplitude of a radiation is emitted is essentially depends on the mass of the reduced mass of the system and the square of the velocity of the system. So, that faster the object goes around, the slower higher the amplitude of the gravitational radiation. On the other hand, you should also note that the frequency of the gravitational wave emitted is coming as a cos omega t and the sin omega t. These two terms, this is coming to be 2 omega t, that is a orbital, twice the orbital frequency, that is saying that the gravitational wave frequency emitted is the 2 times the orbital frequency of the binary system. These two are the important formula for the compact or the 2-point masses emitting gravitational radiation. Their frequency depends on the twice the orbital frequency, and the amplitude depends on the square of the velocity of the system. Okay. So, we have seen the gravitational wave emitted from a toy model, where two masses are going around each other producing gravitational waves. So, this could be a Hertz like experiment in which you have 2-point masses are attached by a stick, and you are rotating with the particular speed of omega, and that emits the radiation. And we know that since the constant involved are very small, we need to go large masses and moving very fast. In the lab, if you even if you use omega of the order of thousands of rpm, you can get an amplitude only of the order of 10 to the power minus 35 or smaller. So, you need to go to astrophysical systems. And one of the systems which are interesting for this is a compact binary system, where two stars which are completely self gravitating system going around each other. So, for such system, you go to center of mass frame, and you can have an effective one body system in the Newtonian case, and you define what is known as a reduced mass in terms of this thing, and then you can show that the orbital frequency, which is we call the Keplerian orbit, is given by in terms of the total mass of the system. That famous Kepler's law, omega square is proportional to mass of the total mass of the system and divided by r cube, that is the separation between them. So, that means that when the stars are very far away, their orbital frequency is very large, and when the stars come close by, their orbital become smaller and smaller. It is the same rule which dictates our solar system, where the planets, outer planets, which has a very large orbital frequency, and when you come to closer and closer as to the sun, which is the Mercury is the fastest planet, because it is the closest planet. The same law is applicable to the binary system. Now, we can calculate amplitude, because omega and r are velocity, and omega is also related. Then you can show that the amplitude emitted is essentially depends on the total mass and the radius of the separation between the two stars. That means, the more the mass is, total mass is, the higher the amplitude of the radiation emitted, and the compact is the object, that is the smaller their separation, larger the amplitude of the radiation which is emitted. So, this essentially requires the orbits of a star to be close by, and each of them to be massive. So, one can see that the energy emitted in this case is also given by the third derivative of the moment of inertia, and that also you can calculate. It depends on the square of the separation and the cube power of the angular frequency. And then most interesting, or in the straightforward way to understand them, is the average power emitted in gravitational waves during one single orbit. That power or the luminosity of the gravitational wave emitted can be calculated, and it is given by this long equation, which depends on the fourth power of the Newton's constant and the fifth power of the velocity of light. This essentially tells you that the masses should be large and the radius of separation between them should be small. So, as a energy emits when the stars go around each other, they emit gravitational radiation and the power lost is given by this equation. This power is coming essentially at the cost of orbital energy and orbital angular momentum, which are emitted in terms of radiation. When the energy is emitted, the system become more and more compact, that means it essentially shrinks. More the energy emit, more the negative tightly bound system becomes, and system becomes more and more compact. When the radius becomes smaller and smaller, the speed of the object further increases, because we have seen the speed is proportional to the distance of separation between them, and the speed also increases, that increases the amplitude gravitational wave emitted, and this leads to runaway process and keeps on going on. So, we will come back to this topic little later. There are many other sources one can calculate and go into details of how the radiation is emitted, but the single and most important equation in this is the quadrupole momentum tensor and its second derivative, which directly connected to the amplitude of the gravitational wave emitted. It is essentially says that if the system is spherically symmetric and collapses, no matter how fast it moves, it does not emit the radiation. I will briefly discuss about the potential alternative sources than the gravitational waves, which essentially includes large mass involved, large motion involved, preferably asymmetric. So, that is essentially what we see in the most of the astrophysical event. One of the most energetic astrophysical event which can be seen almost any a corner of the universe in the electromagnetic spectrum is a supernova emission. Supernova may or may not be symmetric and some mass involved moving, and this could be potential sources of gravitational waves. So, that I will come back to the detail of this a little later after listing all the sources and going through some of them in detail. The second sources are compact binaries, which I have already talked about, how what is the emission mechanism in them is involved. And the third one, an interesting source, is the rotating neutron stars, which is neutron stars are very compact objects which has a size or radius about 10 kilometer and whose mass is approximately few times solar masses, 1 or 2 times solar masses, and these will be rotating very fast. For example, millisecond pulsars are rotating approximately at the frequency of 1 kilohertz. So, these if these neutron stars have some asymmetry or a small mountain on them, when they are rotating fast, their gravity is already very strong and they can emit radiation, and this can tell us a lot about the structure of a neutron stars and what is inside them. So, that is why this source is a one more important source of gravitational waves. Of course, when we think of large motion explosion, the mother of all explosion is a early universe, that is a big bang. Universe itself is supposed to have started with a massive explosion of a big bang. In addition to that, in the early universe there may be several high energy phenomena which are resulting in the asymmetric motion of masses close to velocity of light, can emit gravitational radiation, that is which we call as gravitational radiation from the early universe, which is very similar to the cosmic microwave background, but which is in the electromagnetic radiation. A counterpart in the gravitational wave physics also should be present, and that is another promising source of gravitational waves. Okay, I again emphasize the mechanism and details involving the compact coalescing binaries, because these are the most promising sources of gravitational waves, and these are the sources which are detected by LIGO, and that forms the most important source. These two massive objects, which one of them could be black hole, or both of them could be black hole or neutron stars. They are already masses of few solar masses to tens of solar mass in the case of black holes, and going around with the orbits very close to each other, separated by barely a few hundreds of kilometers, and they can emit gravitational waves. This is very similar to the toy model which I discussed earlier, the two masses going around. In principle, that is a toy model, but when comes to reality, it has several difficulties. So, one of them is essentially what we call is the model is built on Einstein's theory, which is a nonlinear theory. So, the early phase, what we have said, the binary compact earlier model which I showed, was where the separation is large, velocity of are smaller compared to velocity of light. They essentially behaves like a Newtonian system, whereas gravitational wave is slowly emitted, and orbit shrinks because of loss of energy, and their frequency increases, and that phase is called early in spiral, where the frequency increases and the amplitude of the frequency is also increasing. So, when if one plots their frequency and amplitude in this plot, you can see that the frequency which you see depending on the starting frequency at which you start plotting. If you start for the case of detectors like LIGO, which can see from 10 hertz, or earlier LIGO detector, initial LIGO could see only from 30 hertz. It depends on amount of signal you see depending on the starting frequency. If you see at 30 hertz, you will see it for a while before they coalesce with each other. On the other hand, if you start at 10 hertz, you will see lot more cycle, because the lower frequency, the larger in spiral phase you have, and the frequency slowly increases as the time progresses, because the radiation is lost in the gravitational waves, and come closer, move faster, and again emit more and more radiation, and this process goes on. At one stage, the system begin to speed up because of they have come closer, and their velocities can come very close to the velocity of light, and that is where most of the difficulties come. But in the earlier in spiral phase, velocities are much smaller and systems can be well modeled. In this phase, in spiral phase, what you have is the entire model is described by a single parameter called chirp mass, which is essentially a complicated combination of two masses of the stars or black holes or system, and the system, assuming that the process go on, runaway process go on, and eventually star merge with each other. At some stage this approximation would break down, but irrespective of that, you can calculate what is the time it required to merge two stars. That is what we call is a chirp time, and that depends on the frequency at which you start observing the system and the mass of the system. Larger the mass, the quickly they coalesce, and lower the frequency you watch them, much more time you get them to be seen. And also you can express the amplitude coming depends on the chirp mass and the distance to the source and the frequency at which you are observing. These expressions can be obtained based on what is known as the approximation, Newtonian approximation, and somewhat correction to that, what you call post Newtonian approximation. Essentially, you assume the velocity of light is still much larger compared to the speed of these things. So, early in spiral amplitude can be written in terms of their chirp masses and distance to them, overall factor of 10 to the power minus 23. That is a main take home number. If you have a one solar mass chirp mass system coalescing at 100 megaparsec, then amplitude of radiation seen is about 10 to the power minus 23, and that is what you need to be detected. Now, as a system come closer, their velocity increases. At some stage, their velocity can reach very close to the velocity of light. Of course, one need not have to reach to velocity of light to break this approximation used in this calculation. At some stage, which we call is a merger phase, all these approximations break down, and Einstein's theory is essentially a nonlinear theory, and which essentially have no formal way of solving 2 point masses going around each other. So, all the analytical approximation break down, and if one want to calculate the radiation emitted by this system, one has to use the numerical approach, and this new emerging field, which is now becoming more and more popular, is known as numerical relativity. In numerical relativity, you solve essentially Einstein's equation. For example, the gravity, if you follow Newtonian theory, then you have a simple equation to solve, which we call as a Laplace equation. For a given boundary condition, you can solve this with the proper techniques, and it is a completely linear system, and one can solve them exactly in principle. On the other hand, Einstein's theory is much more complicated. You have 6 nonlinear partial differential equations. There is no formal method to solve, you have to evolve them in a self consistent manner. In addition to that, you have singularities, and time of evolution and other frames are also not well defined. So, that makes it numerical relativity itself is a very hard task to study, and that is where you have a entire branch slowly evolving. Currently, they are able to solve the Einstein's equation. Approach taken here is essentially you take a time slices or some kind of a splitting you do 4-dimensional space into one evolving in the time direction and other in the spatial direction. You consistently evolve Einstein's equation, set the initial condition, and then slowly evolve them. There are equations are complicated, but essentially you eventually when you evolve through all the time slices, you get the full evolution of system, and then you can compute the entire waveform. And numerical relativity is essentially needed to solve the Einstein's equation in this merging phase. And current days this can be done for the systems such as GW 150914, and similar systems can be evolved numerically, and one has a understanding what the waveform look like that in that phase. The last phase is what is known as a ring down phase. When two black holes or neutron stars or whichever star is merged and forms a single object or a black hole. It is a highly distorted black hole which would slowly dissipate all the energy which is supplied to it in terms of quasi normal mode, and that is damped system which dissipates all the extra energy and settle back into Kerr black hole. So, that whole process is called the ring down phases, and this essentially can be calculated based on the black hole perturbation theory. The ring down is studied essentially in the black hole perturbation theory. You take a black hole, favorite black hole, either Kerr black hole or Schwarzschild black hole, perturb them using a given system. In this case of binary coalescing system, you may be merging two black holes, and the resulting black hole itself is a highly disturbed. Or you could have a system, black hole is disturbed by the neighbors, you hit them with the fields or hammers or whatever appropriate, and see what is the resulting system behaves, and that is what you call, you know that the black hole behaves like a bell which rings for a while with the damped sinusoid with the definite frequency which characterizes the properties of black hole, and this damped sinusoid slowly dies down and then it settles down to Kerr black hole. So, these are called the quasi normal modes or ringing downs of black hole. So, this was predicted first by an Indian Professor C.V. Vishweshwara. So, in a given inspiral ring merger down system like GW 150914, this is essentially is the power in the each of the band. Though in the inspiral phase amplitude is very small, you will have the duration very long. The merger phase amplitude is very large, but the duration is very small. On the other hand, ring down amplitude is very small and often very hard to see or recognize them. So, that is what you have in the entire what we call is the inspiral merger ring down, which can be completely simulated based on the numerical simulation. On this slide, we show a movie of generated based on the numerical simulation of two black hole. Initial phases, you see black hole going around each other very slowly, their amplitude slowly increases, frequency increases and so on. At some stage their amplitude increases, comes down, merges into form a single black hole, and the remaining black hole will be oscillating for a while and then settle back to binary quiet Kerr metric. So, this is essentially a story of a black hole merger or black hole binary system, what we have seen in the LIGO band, several of them now, starting from first event which had a mass of nearly 30 and 35 solar mass merged together to form a single black hole of 62 solar mass black hole. Okay. So, we will continue with the gravitational wave emitted by point systems or binary system which are going around each other. Most spectacular things such as black hole going around each other and emitting radiation. One can also calculate the power emitted by this system using the formula given. They are given for each orbit, but one can successively integrate over all the orbits and find out how much energy is emitted. For example, black holes such as GW 150914 has emitted the energy equivalent of 3 solar masses. So, you have two black holes of masses 35 and 30 solar mass merging together, forming a single black hole of 32 solar mass, emitting radiation equivalent to 3 solar mass. These are very energetic events, very bright event in the universe. However, you do not see them because it is not emitted in the electromagnetic radiation. These are emitted in gravitational radiation, which is weakly interacting with the material. And what we collected, seen amplitude only of the order of 10 to the power minus 23, and it is come down. So, overall all these energy is emitted only about in 0.2 seconds, and if you see that amount of energy so much emitted, these are some of the spectacular events. However, electromagnetic bands you almost do not see anything, because black holes are essentially point object and there is no other visible matter around them. So, you cannot emit any radiation, electromagnetic radiation. Gravitational radiation we have seen, but it is completely silent in the electromagnetic band. On the other hand, if you have a binary stars, compact binary stars made up of neutron stars, then in addition to gravitational waves, you could also have a very spectacular display in the electromagnetic band with the various frequencies from gamma rays to radio waves. So, that is what happens when the two neutron star merges. They also go through this inspiral phase, merger phase and ring down phase. The resulting object may or may not be black hole, that depends on their mass and equation of state. Neutron stars are very fascinating objects. LIGO has seen this in spiral. The first source of binary neutron stars was GW 170817, and which has followed up by entire electromagnetic spectrum. On the other side, neutron stars are astrophysically very interesting object. I have told earlier that they have a mass about 1 to 2 solar masses, and the entire star has a size about 10 kilometer, completely compact dense stars. Now, the one of the mysteries of neutron stars, what we call is what these neutron stars are made up of. They have a matter, so we expect them and we have seen it in the entire electromagnetic band. So, the one would model them as these three phases: in spiral, ring down, and in spiral, merger and ring down. One can model the system and understand what is inside the neutron stars. So, that is still a mystery. What we call is the equation of state, or what the neutron star is made up of. It is based on the various models. There are various relation between what is astrophysically observable and what cannot be observed. On the other hand, gravitational waves gives you another independent information. It is like watching in another channel, and you see another news channel, independent observer, and you can extract and match with the model. So, what do we have seen and what do we expect to see in the more neutron stars, and one would like to see is what we call is a equation of state, what neutron stars is made up of. This is mainly coming because of the tidal distortion. In the case when the stars starting from in spiral phase, they are very far, very far in a relative sense compared to their size, and then as they come closer and closer, their gravity becomes stronger, and one star would tidally distort another star and pull their material, and as the system merges, the star is distorted and then merged and form a single structure, may be a highly unstable neutron stars, which may further collapse into a single neutron star or black hole. So, one would like to model this system and try to constrain the equation of state based on the quadrupole induced distortion. That means, when the star come closer, each star will distort another, pull up their material, and the amount of distortion produced depends on the structure or equation of state of the neutron star, and that we believe would happen approximately a frequency of about 400 hertz. So, that is where the stars could distort one another and see how much they can distort. There are many equation of states which allows various different sizes and shapes of neutron stars. Here the idea is that in the various equation of states, you see how the stars are distorted and how much is the distortion they can produce, and whether these tidal distortion can be constrained based on the observation of neutron stars. So, that is what being plotted here with the different equation of states and the distortion parameter. It can essentially say that some of the models do not produce enough distortion, or they are not sensitive to them. On the other hand, some of the models can be well constrained based on this. So, that is essentially what you see. Kerr parameter or angular momentum per masses with respect to mass. One essentially means black hole, where it cannot have any tidal distortion. On the other hand, when you have more and more a value, you have a more and more distortion. However, given a single merger, these models may not be well constrained, because you have enough signals, and you may not be able to constrain your parameters where you want them. On the other hand, people also have studied, if you have enough observation, let us say that over the year you are observing about 30-40 events of neutron stars mergers, and then based on their combined data, whether one can constrain particular equation of state, and one sees that can be done. In addition to that, we have seen that with the current model, we have seen that we have seen a single binary neutron star, that is GW 1708-17, where two neutron stars, one approximately has a mass of 2 solar mass and another is slightly smaller, merged to form a neutron star, which was simultaneously close to that seen in the gamma ray band, and which eventually tell you entire model of how the merging of neutron stars and eruption which comes out star interact with the interstellar medium and produces various electromagnetic radiation and combine all the data and form a multi-messenger astronomy and constrain the full model of the system. So, that is going to be the exciting and future gravitational wave astronomy, supplementing the entire band of electromagnetic waves and forming a model which can constrain the neutron stars and neutron star system. So, another when it comes to neutron star, there could be another source of radiation, that is called the single neutron. Again, neutron stars have a mass of approximately about 1 to 2 solar masses, and their size is of the order of tens of 10 kilometer. Now, they will be moving at the speed at the frequency about 1 kilohertz or less, or it's one can expect a small deformation on the surface of these stars. For example, you could have a small mountain, imaginary mountain on the neutron star, which essentially a quadrupole moment produced. A clean rotating star would not have a gravitational wave emitted, because there is no time varying quadrupole moment. If you produce an asymmetry or a distortion, for example, a mountain, then the structure produces a time varying quadrupole moment, which can be plugged into quadrupole formula and obtain the gravitational wave emitted. In this case, the object is rotating with a particular speed or frequency, and you would see that they would be emitting a monochromatic signal with the frequency twice that of the orbital frequency, not orbit, actually its own rotating frequency. So, this is LIGO is continuously looking for these neutron stars rotating about its own axis, and what is known as a single neutron stars. And one can also see several of the pulsars, which are essentially neutron stars, which has a radio beam pointing in our direction, and which we can estimate their orbit, not orbital, rotational frequency, and based on their mass one can calculate where do these signal form, whether they form in the detectable range or not detectable range. All the known pulsar can be put in terms of LIGO sensitivity curve. For example, this plot shows the frequency of the detector or the gravitational wave on the x axis, the strain sensitivity of the gravitational wave detector on the y axis. You have a initial LIGO, advanced LIGO and future detector, and you can put all the neutron stars, whatever information you know about them, you know their frequency well. So, that makes it essentially you know where exactly to be seen. Amplitude is depend on the amount of distortion. If you are not able to see the source in the detector, that means their distortion is highly constrained, and one can constrain the various model which can cause a distortion in the neutron stars. You can see several of them would be just in the boundary of detectable region with the current detector. Maybe in the future you would also see the rotating neutron stars in the LIGO detector. So, this leads to some of the mechanism by which one would like to understand how dense objects such as neutron stars can be distorted. The one of the mechanism could be magnetic fields. If you have a magnetic fields around the neutron stars, strong magnetic field, and that can cause certain amount of distortion. You can have an accretion disk which is dumping matter onto neutron star and distorting them. The pulsar which are again neutron star, which has a well known phenomena known as glitches, though it is very hard to understand them. The star itself undergo a change, and its frequency changes with the glitches, and then resulting it settles down to another state, and that event also might be resulting in the gravitational waves. And then you can have a magnetic flares, magnetars, which has a very high magnetic field of 10 to the power 15 Gauss, and can cause some internal structure modification, and resulting in the glitch. One may able to study or constrain all the these physics or the models which can produce the distortion. That is about the point sources and gravitational waves. Another interesting sources of gravitational wave is the stochastic gravitational wave background. The stochastic gravitational wave background can be of two nature. One, there could be large number of stellar gravitational wave sources like binary neutron star, binary black holes and so on. Many of them may be so many of them you may not be your detector may not be able to distinguish individual sources, or there may not be enough signal in the individual sources to be individually identified. So, this leads to a background of radiation which is coming from the astrophysical binaries. So, those will have a distribution based on the local binary population, how many of the stars can produce with the right reserve band and so on. The more interesting source would be a cosmological stochastic background. Like in the early universe, as told earlier, there could be many energetic events which would be leading to high velocity motion, large mass moving at the this thing. So, those all, if there is no specific pattern in the motion if the involved, then you could have stochastic gravitational wave generated from the generated in the early universe. All of them is essentially characterized by a parameter called omega GW, which is essentially related to the density of the gravitational or density of the system in the early universe, which essentially leading to an asymmetric motion and emitting to the contributing to the emission of gravitational waves. All these stochastic gravitational radiations are characterized by their power spectral density, or they are essentially considered a noise above your system noise or detector noise, and this is essentially characterized by a power spectral density which you relate to your physical parameter, which is in this case is omega GW this thing, and the frequency which you can essentially track back to the gravitational wave detector. Now, there are various models and physics which leads to emission of gravitational waves, and they can be plotted their contribution on the detector response, as we have done it for the neutron stars and so on. Here on the x axis you have a frequency, on the y axis some kind of a representation of power or involved, or essentially amplitude of gravitational wave in that frequency band, and various detectors is also plotted. You can see the binary neutron stars or binary black holes which contribute certain power spectral density. Is also neutron stars, if there are large number of neutron stars which have a R mode instability. This is one of the instabilities inside the neutron star, which is causing matter to move in a non-axially or toroidal fashion, and they can emit gravitational wave. Even if you assume that neutron star, 1% of these newly born neutron stars have a instability, and then you could leads to a background. There are other leads to gravitational wave sources too. The population star collapse, neutron stars and the supernova collapse, black hole neutron star merging, and various instabilities in the neutron star also leads to these things. So, essentially this contribute the most of the galactic binary systems and waves emitted with them plotted as instrumental noise and